Thank you. Good afternoon, everyone. My name is Ismael. I'm one of the co-founders of Lagrange Labs. So the title of my talk today is Giving Every Smart Contract a Verifiable Database. A very bold statement, but the culmination of a lot of the work of our team over the better part of the last year, building our circuits, our proving system, our proof constructions, and then our network of provers. So to start with, we're very excited to announce that next week we'll be coming to market with our Euclid testnet, which is the first version of our verifiable database and our coprocessor. What makes Euclid special? Well, it's a different approach to coprocessing, specifically to coprocessing for very data-centric and data-heavy applications. And we're going to get into that very shortly of what makes this approach very unique and very well suited for certain things you would want to do on a blockchain. So, to start with, there's a very simple design premise that we hold core to how we build our applications or our networks. The key is, when we think of computation over on-chain data, it's a twofold question. It's not the question of how do I go run a bunch of inclusion proofs over an MPT tree and do that very, very, very fast. The question is, how do I pre-process, transform the underlying data of a blockchain into a query-friendly format, such that I can continue to manipulate that data at scale and can verifiably compute over that. And so this really kind of boils down to two core steps. The first is pre-processing, which is taking the data within the MPT tree, encoded with Keccak and RLP encodings, and proving its equivalence to a ZK optimized data structure containing some subset of the elements within the MPT tree. So think of a given contract, a mapping, for example. You want to instantiate a database over your NFT mapping, over your ERC20 ownership mapping and balance mapping. What you want to do is to take the portion of the blockchain data that corresponds to all of those leaves, and you want to transform that into now an optimized structure. You want to index the chain, you want to extract the relevant data, and you want to prove that a new structure created from those leaves is equivalent. It contains the same elements, there's nothing been censored from it. And then once you have that optimized structure, let's say it's now a Poseidon 2 binary Merkle tree, you want to execute computation over that verifiably. Because if I was to say, and I think this is probably self-explanatory to everyone in the room here, I'm going to run my circuit over an input of a binary Merkle tree, and that's the commitment I'm going to use for my data. It'll be much faster than trying to compute Keccak and RLP encodings for those same subset of elements, especially if I want to go over the time aspect of the chain as well, and I want to go back some deterministic number of blocks. And so, how do we do this? How do we prove the equivalence between two data structures such that we can later query those efficiently? This is based on a vector commitment our team proposed last summer, and we've since submitted a paper to CCS where it's been accepted, called RECL trees. RECL trees are a vector commitment based on combining recursive snarks and Merkle trees. So what makes RECL trees special? Well, the core property is that they are updatable, which means that if you change some subset of elements within your RECL tree, you can update the batch proof of those elements in logarithmic time. So not proportional to the size of the data set, but proportional to the number of updates. Now, the core innovation behind this is something called canonical hashing, a deterministic algorithm for representing some subset of nodes, so some subset n of k leaves, in a set of a tree, such that we can define the set of leaves anchored below every branch node in a way that allows us, when one element changes, one leaf changes, we can only update the canonical hashes along the path that have changed as well. And what this lets us do is to have two properties. Firstly, highly parallel proving as we compute the canonical hashing for every branch node, and updates. So compared to the state-of-the-art works like hyperproofs, Merkle snarks, and then our previous work, rec proofs, that we positioned last summer, the RECL tree construction was substantially faster on proof time and was substantially faster on updates. And so what we then decided was, well, what if we take the same construction of RECL trees, and we apply another layer of computation on top. We call these RECL plus trees. In a RECL plus tree, a prover commits to some memory M and proves the correctness of both the inclusion of the leaves within that commitment and the result of a map-reduced computation over that subset M. What this lets us do is something called digest translation, looping back to how this lets us build a verifiable database. Digest translation lets us prove that two digests are the same by constructing our canonical hash in a way such that it equals the output of the second digest. What we can do then is take two data structures with different arity, different hash functions, different branch encodings, and we can prove that they are equivalent. In essence, we can take what is a linked list of MPT trees, a blockchain, and we can prove that some subset of the elements encoded in there are equal to some new commitment. And so what we found when doing this is, due to the parallelizable nature of our construction, we're able to construct these batch proofs orders of magnitude faster for digest translation applications than any former state-of-the-art approach. Updates are also substantially faster as well, which means we can create these verifiable databases over large portions of the MPT tree, and then, when requested and when required by a new block coming in or some subset of elements mutating as a result of a transaction execution, we can update those databases. And so what this lets us do is to take the portion that we want to compute over the MPT tree for our coprocessor, and we can pre-process that and extract it. And we can transform that into a data structure that makes our queries very, very fast. And so we've talked about how we do it and talked about why we do it, but we haven't talked about what we transform into. So the way we think about it is that there's 3 core tables that are contained within every blockchain with respect to storage tree. There's a storage database or storage table, state table, and then block table. And so the way we do this encoding is we take all the values that we care about from a given contract for a given row in that table, and we encode those into a given branch with, we code those as leaves under a given branch with the arity equal to the number of columns. We then encode every column as a separate, every row as a separate branch at the second layer of the tree. We then we then have a layer we call the state database, which is a commitment to all of the contracts within a given block that we do this extraction and transformation for, and do this pre-processing for. Finally, we have a time-dependent table on top of this, which we use to link between the state, storage, and the block number. What this gives us is a final structure that we can compute over that doesn't require us to run a proportional amount of computation to the depth of historical state you're going back to look into. It's only proportional to the size of the table. And it also gives us the opportunity to run all of these inclusion proofs over a structure of a fixed arity in a single tree. By doing this pre-processing, we can functionally amortize the cost of queries across every single, across the cost of pre-processing. So we only have to pre-process once, in essence, in order to run an arbitrary number of queries over that table. And so looking at the developer flow of this, there are really 2 steps that you have to do. You have to first instantiate a table, and you have to then second, you have to structure queries that you can run over that table. And this will be a developer flow that users can start interacting with as of next week with our testnet. So, firstly, we have a contract standard that you can deploy alongside your, within your contract that lets you define what the data schema you want for your table. What are the variables, what are the mappings, what are the arrays, what are the objects, and how do you want that structured? Do you want this ordered in a certain way? Do you want some set of elements excluded? Do you want to have separate tables? We give you a lot of flexibility there, and this flexibility will only improve over time. Once you define how you want your data to be structured and the data you want to be extracted and pre-processed for you, you define a set of queries, where each query corresponds to an event that you emit when you want our off-chain network to return a proof of that query to you. And obviously that contract, when they return a query, we'll call our verifier and verify both the equivalence proof of the transformation and the result of that query on top of the transform data. And so next week, we'll principally be doing select queries, which are simple and very intuitive to understand. But this will open up very soon to a much larger set of operations that will allow you to prove in SQL, including things that have otherwise not been possible, things like joins, complex aggregations, etc. And so what are the asymptotics of this, and then what are the benchmarks we have? Well, the pre-processing can be done, the proving time for a high degree of leaves can be done in generally about 75 to 80 seconds, scaling logarithmically with respect to number of leaves. So we can basically build tables of 100,000 leaves per block with about 80 seconds of setup time. And then update times are proportionate to the number of changes that happen per block. So if you think of a stored structure like, let's say, the ERC20 contract for USDC, there's maybe 50 to 100 updates per block. And so that can kind of give you roughly the time it takes to update the table every time a block comes in. Given that these are longer than block time, in the current version, we batch these together to do a group of updates for a group of blocks at once. And now, how we structure queries is based on a MapReduce format, where we're able to execute all this computation in a fundamentally parallelizable way, and we can then recurse those proofs back together such that we have a final proof showing the validity of some data parallel computation over some input commitment. And so because this is highly parallelizable, we have our distributed proving architecture, which will be deployed very soon on EigenLayer as an AVS. And we have we announced a few weeks ago about 2.5 billion of commitments behind securing the liveness of this prover. And so what this lets us do is to structure very, very large computation and benefit from having workers commit to a small portion of this parallelizable computation and then serve that proof back within a requisite period of time in order to receive a reward, with slashing occurring if they don't serve the proof back within the time they committed to. And so once we think about these queries, we have very, very fast query performance as well over the transform data. So once you have everything in your transform structure, you can start accessing far more leaves per query than you could traditionally touch with a normal storage proof, where you think of the state-of-the-art solutions maybe let you touch 500 leaves, and within Ethereum block time, we can touch about would be 100,000 rows over 10,000 blocks. So that will be about 10 million storage slots within about 8.9 seconds. So we can start structuring very, very large computation of the transform data by paying that one-time upfront pre-processing cost. And this obviously scales very, very well when you have very frequently touched areas of the table that you want to structure computation over. So if you think of the blockchain data broadly, there's only a subset of contracts that users typically interact with, right? We can enumerate those. It's going to be Uniswap, lending apps, frequent tokens contracts, and then the majority of the chain you can think of as the telomeres of the blockchain. There's just dead space of contract people deployed in addresses that people don't really use. And so by structuring pre-processing over the highly used parts, we can support very, very cheap queries when required over those areas of the blockchain that people actually use. So we had a bunch of recent announcements that I'm going to summarize for folks, as well as kind of the next steps and the future directions that we're moving towards. So we announced our RECL tree paper, and we released the code base of that in mid-March. The Euclid testnet, V0 of our verifiable database and coprocessor, are coming out next week. We have a production release actually a little bit later today on another one of our products called State Committees, which will be going live on EigenLayer. And then in May, we expect to have production for our Euclid database on Ethereum. So thank you all for listening. Hopefully people learned something new. Any questions?
Hey, Ismael. Nice talk, nice work.
Thank you. Thank you, Alan.
So you had a slide with numbers for proving. Can you go back to it?
For RECL trees?
Yeah. Update. This is the update.
There we go.
So what are you proving here?
Yeah, so we're proving the inclusion of a batch of a specific size within a tree of a specific size.
I see. So compared to hyperproofs, which use an IPA, you're using Plunky 2 in Recl trees, or what are you using?
Yeah, we're using Plunky 2 in the first
Plunky 2.
implementation.
And that gives you a speed up over IPAs?
Yes, generally because we can parallelize it much better. We can distribute it across a very large machine.
I
large
see.
distributed network of machines.
So these are multi-threaded benchmarks?
Well, it would be, I guess, we would be looking at hyperproofs multi-threaded, I believe, versus Recl trees, which would be multi-threaded and distributed. So we have actually benchmarks for single runs and distributed runs. And so I guess one of the properties that we can do with Recl trees is we can actually distribute them across a high number of machines, which isn't a property we have in hyperproofs. So that gives us a substantial speed up there.
I see. So interesting. Okay, we're going to have to beat that later. It's unacceptable that a snark beats hyperproofs. But thank you.
Yeah.
Yeah, it's here. On this side. Right, yeah.
Yeah.
On this side, yeah.
Oh, yeah.
So I'm mostly interested in, so this is, I suppose the use case with this is to, one point I saw you mentioned is to amortize the proof cost, right? So when you can't, when you have an update to the state, then you don't need to pay for the proof cost of the states, before. Do you think this has use outside of just the update of blockchain? Can I use this as a general, like build a data, like a ZKP database?
Yeah, I mean, I think you
general,
could.
Like,
I think you could. I think the things that we build are agnostic to what those tables are. We functionally build mechanisms to map between arbitrary data sets and tables, and then ways to prove general purpose SQL computation over those tables. I think in terms of the application of that, we're very focused on the application of that on blockchains, since effectively the security of your proof will always be based on the authenticated data structure used as input, right? And so I think the perspective we have is that the consensus of most of these chains creates a very high degree of safety over the veracity of whatever data structure you're using as input. And so you actually have just a very large existing set of these data structures that have a very high degree of economic security behind the state transitions and the updates to them. And so we can basically piggyback on those economic guarantees to be able to have additional tables and structures you can query directly from the blockchain. But if you have another structure you'd want to load in, then your security would be based on whoever does that loading.
right, like the blockchain is a time-stamped, like a ledger.
Exactly.
So if you have this, you can probably build an application out of like a general ledger, like.
Yeah, like taking Postgres.
Yeah, like something like this completely decentralized ledger.
Yeah, you could do that.
Non-blockchain.
For sure.
Very,
you could do that. Yeah, and you could load that in here for sure.
Very exciting.
If you're working on that, we'd be open to.
Sure. I'll
collaborating.
definitely talk to you. It's very interesting technology.
Yeah.
Thank you, Ismael.
Thank you so much, guys.